All right, friends, welcome back. Hope you had a great weekend. I just realized the iPad is running at like 1%, but it's plugged into the computer, so we're just going to hope for the best. And if I have to use chalk, we'll probably just say we're done for the day, because who wants to use chalk? All right, so we have basically covered what you need to know for the exam. What we're doing today is starting in on Chapter 8, which I know you don't care about because it's not on this exam, and that's fine. But at least you're here, and then once you've started to care about Chapter 8, you can come back and rewatch this lecture anyway. Chapter 8 is interesting because we tell you something that's been going on the whole time in the background with substitution reactions, and it's these elimination reactions. And what we talked about just at the very end of class last time was how that because of hyperconjugation, some of the LUMO in an alkyl halide, sorry, I'm trying to, okay, that's too loud. I'm trying to adjust the volume. There we go. Because of hyperconjugation, some of the LUMO in an alkyl halide or a molecule with a leaving group is actually also spread out onto the beta hydrogen or the beta proton. And so a nucleophile, when approaching a molecule with a leaving group, is going to have a choice. Do I attack the LUMO at the carbon, or do I attack the LUMO at the hydrogen? Of course, if we attack at the carbon, that's backside attack, and that gives us substitution reactions. But if we attack at the beta proton, what ends up happening is this elimination reaction where we remove the beta proton. The electrons that were already partially delocalized towards the alpha carbon dump completely over to make a new pi bond, and the carbon leaving group sigma bond breaks. And that's all in the same step. And that's what we call an E2 reaction. And we're going to need to deal with how a nucleophile or a base decides whether to attack at the carbon or the hydrogen. The basic principle is a good base will prefer to attack at the hydrogen. A good nucleophile will prefer to attack at the carbon. Some things are going to be both good bases and good nucleophiles. Some are going to be one or the other, or neither, and we'll figure out how to deal with that. But you need to be prepared to anticipate the possibility of an E2 reaction, which can occur whenever there is a proton adjacent to the leaving group. Now, there's a couple of requirements. Well, one requirement for the proton that's adjacent to the leaving group, and it really has to do with this hyperconjugation thing. Hyperconjugation works and puts LUMO on the beta proton only when the beta proton can be lined up with the sigma star. So if we were to do a Newman projection and sort of look down that carbon-carbon bond, sorry, can't resist. I'm just going to do, yep. He hates Obi-Wan. So if we were to look down that carbon-carbon bond, in the back we would see the bond between the beta and the alpha carbons with the beta carbon in the front. In the back we would see the alpha carbon with the C carbon bromine sigma bond pointing downward. There'd also be the implied hydrogens pointing there. And then we've got this hydrogen that's, from our perspective here, pointing straight up. And this is the one that has the LUMO on it. And then there are two others oriented this way. This is the beta carbon, the alpha carbon's in the back. And LUMO only spreads out onto this beta proton when it is lined up with the sigma star. So there's this requirement for hyperconjugation that the filled orbital has to line up with the empty orbital. I'm going to try to represent that just by filling in the colors in the drawing that we have over on the left. Here would be the node between the two nuclei, and so on. Okay, so this required arrangement in space between the beta proton and the leaving group is called anti, which should make sense because we've talked about groups being anti in various conformations. Anti-periplanar, that means they occupy the same plane. They're all lined up on this plane, but the two bonds are anti to each other. And that is a requirement for the E2 reaction. The LUMO only goes on the beta protons that can be anti to the leaving group. That's going to be important. We're going to test your understanding of that. That opens up some interesting and weird stereochemical issues that you need to be aware of. Okay, some other things to know about this elimination reaction is that the reason it's called E2 is because the base and the alkyl halide show up in the rate law. It's a single reaction step. If we drew an energy diagram, the energy diagram for the E2 reaction would be very similar to the energy diagram for an SN2 reaction. That is, the base removes the proton at the same time as the carbon-carbon pi bond is forming, at the same time as the leaving group's breaking. One rate determining step, both the base and the electrophile show up in the rate law, which is where the 2 comes from. There's 2 concentration terms in the rate law. All right, questions so far? Anything I've missed there? Go ahead.
The 2 orbitals have to be out of phase.
So do the 2 orbitals have to be out of phase? What I showed you last time is what happens, where is it? There we go. In hyperconjugation, when the filled orbital overlaps, sure, close enough. When the filled orbital overlaps with the empty orbital, you get a plus combination and a minus combination. The plus combination has them in phase, and that's where the electrons are. And then the LUMO, the minus combination, has them out of phase. And so that's what I'm showing you. I'm not showing you the other plus combination that exists. All right, oops, sorry, got to get back to where we were. There we are. Other questions about sort of E2? Okay, just remember the leaving group has to be anti to the beta proton in order for the reaction to happen. Now, if we come over to the other side, we've seen that a carbocationic intermediate, which is what you get after the leaving group leaves, also has hyperconjugation in it. You have the empty p orbital that's adjacent to a carbon-hydrogen bond. This is a diagram of the LUMO, the empty orbital that's spread out a little bit onto the beta protons. And we've said that a base or a nucleophile, when it sees a carbocationic intermediate, can choose to attack at the alpha carbon where the positive charge is, or at the adjacent beta hydrogen. And again, bases are going to prefer hydrogen, nucleophiles are going to prefer carbon, but if we attack at that adjacent hydrogen, excuse me, there we go, no, still struggling. If we attack at that adjacent hydrogen, then we break the carbon-hydrogen bond, the electrons in that bond dump into the empty p orbital, and we create a new pi bond. And so we call this an E1 reaction. It's an elimination reaction in the sense that we made an alkene. I didn't show you the step where the leaving group leaves because that's the previous step. It's called unimolecular because you will see that exactly like the SN1 reaction, the rate depends not on the concentration of the base, but only on the concentration of the electrophile. The reaction diagram looks like this. We have 2 steps. This is the transition state of the rate determining step. And importantly, this first step is basically the same for SN1 and E1. So the same first step, the leaving group leaves, and then we get the carbocation. What we'll see in general is that SN1 and E1 always compete. That there's not great selectivity for SN1 versus E1. So in other words, whenever you predict that an SN1 reaction is going to happen, you must also account for an E1 reaction happening. The idea is that the carbocationic intermediate is high enough in energy that the two pathways you have, attack carbon or attack hydrogen, are very, very similar. There's not a huge difference in rate between those two options. So you expect always to get a mixture of SN1 and E1 products. All right, and we'll deal with that in some examples. All right, so that's our overview. For the E2 reaction, it is going to matter whether our nucleophile is a good nucleophile and whether it is also a good base. But we will see that for the E1 and SN1 reactions, it doesn't matter that SN1 and E1 always compete. So let's summarize some things we know about good nucleophiles, and then we will add things we know about good bases. We've said in general, good nucleophiles have conjugate acids with pKa's greater than 0. Good nucleophiles are generally negatively charged. And we developed a list, but you can look at a pKa table and see things that are good nucleophiles. For example, we would include CN-, whose conjugate acid's pKa is around 9. We would include a carboxylate, whose conjugate acid's pKa is around 4. We would include hydroxide, whose conjugate acid's pKa is around 16. We would include alkoxides, like methoxide, whose conjugate acid's pKa is also around 16. We would include things like this deprotonated alkyne or an acetylide, whose conjugate acid's pKa is around 25. All of these are good nucleophiles. The category of good base is going to overlap somewhat with molecules that are good nucleophiles. Molecules that are good bases in general will have conjugate acids with pKa's greater than or equal to 16. So you're going to see some of the items on our list above for good nucleophiles are not going to show up on our list of good bases. For example, you would predict CN-, good nucleophile but not a good base, because its conjugate acid's pKa is 9, and that's less than 16. Similarly with the carboxylate, you would predict a good nucleophile but not a good base, because the pKa of its conjugate acid is around 4. So things that show up as good bases and good nucleophiles are going to be things like OH-, MEO-, ethoxide, which is this, and acetylide, anions, deprotonated alkynes. So, yes?
Is it safe to assume then that all good bases are also good nucleophiles?
Is it safe to assume then that all good bases are also good nucleophiles? And the answer is almost always. Okay? So let's just deal with that right now. Is it possible to be a good base but not a good nucleophile? And the answer is almost never, but there are a few cases. And to set this up, one of the things you have to realize is that hydrogen is smaller than carbon. And so that gives you a potential route for selectivity in deciding whether you're going to have something that's a nucleophile or a base. For this alkyl halide here, the carbon in the middle is the alpha carbon, the one that bears the leaving group. The carbons on the edge are beta carbons, and you can see the protons that are anti to the leaving group. That'll become clearer if I go to the ball and stick model. You can see in front there's a proton there that's anti to a leaving group. I'm going to return to the space filling model. You could imagine a sterically hindered base that might be large enough that it can't actually get in towards the alpha carbon, but it could attack the adjacent beta protons. The beta protons are less sterically hindered than the alpha carbon. So in organic chemistry, we do have a few molecules that are sterically hindered bases that can't attack the alpha carbon and therefore can't do substitution reactions and are therefore poor nucleophiles. It's like based on pKa considerations, you'd expect them to be good nucleophiles, but because they're so sterically hindered, they're not. So the classic example of this, the most important example of this, is the following sterically bulky base. We call this tert butoxide. It is the conjugate base of tert butanol, which is one of the isomers of butanol, tert referring to the fact that you've attached the OH to the tertiary carbon. Tert butanol has a pKa of 19. It's a little bit higher than expected for an alcohol. And based on that criteria, you would say that it falls squarely into things that you would expect to be a good nucleophile and also a good base. However, tert butoxide is not a nucleophile. It is only a good base, and the reason for that is steric hindrance. If we could draw a space-filling model of tert butoxide, you would see that those branching methyl groups would make it very difficult for that oxygen to approach the carbon that has the leaving group. Okay? There are two other bases that are in this category. You can see their structures in the textbook in chapter 8. I'm trying to figure out whether it's worth our time to draw them, and I think the answer is no. Though we hate to just memorize acronyms. These are going to show up in problems in your text, so I do want you to be aware of them. I don't actually care that you know or memorize their structures. But there are two additional sterically hindered bases. One of them is called DBU, and the other is called DBN. They have this interesting structure of a six-membered ring with two nitrogens in it. And the nitrogen that's involved in the pi bond with the lone pairs is the basic nitrogen. And then attached to that six-membered ring, in the case of DBU, you also have a seven-membered ring. And, oops, yep, that's fine. And in the case of DBN, it's not a seven-membered ring, it's instead a five-membered ring. So naturally, you don't want to memorize those structures, and so I'm not going to make you. But the idea is this is the basic nitrogen, and it is sterically hindered. It would be difficult to for that nitrogen to attack an alpha carbon. So these are all sterically hindered bases that are only good bases and are not good nucleophiles. So tert butoxide, you can sort of get that from its structure. DBU and DBN, if you don't know the structure, you're just going to have to memorize that those are sterically hindered bulky bases. Okay, so questions about that? So if you look, we're going to have between pKa's of sort of conjugate acids between 0 and 16, you're going to have things that are only good nucleophiles. In the range of 16 and higher, you're going to have things that are both good nucleophiles and good bases. In the range, and we're going to forget about pKa when talking about things that are only good bases because of sterics. Sorry, that's terrible penmanship. And then, of course, you have things that are both weak nucleophiles and weak bases. And these are going to be things whose conjugate acids have pKa's that are less than 0. So that would include water and alcohols. All right. Okay, so 4 different categories. You can be a good nucleophile and a good base. You can be just a good nucleophile. You can be just a good base because of sterics, and then you can be weak at both. Having those in mind is going to be really useful as you try to decide what the outcome of various reactions are. Okay. All right. Let's talk about how the rate of the E2 reaction, the elimination reaction, depends on both the nucleophile and the electrophile. So first, because the rate is dependent on both the concentration of the base and the concentration of the alkyl halide, we will say that E2 is favored by good bases. Duh. And that means something whose conjugate acid has a pKa greater than or equal to 16. The second thing is the rate depends on the structure of the molecule that has the leaving group. And you're going to see that this rate is the rate dependence on the structure of the alkyl halide, or the molecule with the leaving group, is backwards from what you expect for SN2. So there are a couple of issues. The first issue is the availability of beta protons. And then the second issue is the stability of the alkene that is formed by the elimination reaction. So let's illustrate this just with some examples. A molecule methyl with a leaving group, can it do E2? What does that molecule lack that E2 requires? You don't know. Let's go back here. What does methyl leaving group lack that this molecule has? Beta protons, right? No beta protons, no elimination reaction. Right? So the methyl, there's no E2 because there's no beta protons. All right, so for a primary leaving group, you have 3 beta protons or one kind of beta proton. It turns out that E2 for the primary leaving group is relatively slow. It gets faster if there are, for a secondary leaving group, in which you can see we have even more beta protons, so 6 instead of 3. So it's a little bit faster for secondary alkyl halides. And then for tertiary alkyl halides, it's quite fast. And I won't draw out all those CH bonds, but we'll say that it's very fast. E2 is very fast for tertiary alkyl halides. It's fast for 2 reasons. First, tertiary alkyl halides have more beta protons. But we can also talk about this in terms of the alkene that is formed in the elimination reaction. In the elimination reaction of a primary alkyl halide, the alkene that's formed tends to look like this. It tends to have a lot of hydrogens on it, okay? Whereas for a secondary, an E2 reaction for a secondary alkyl halide, there tend to be more non-hydrogen things attached. And for a tertiary alkyl halide, there would be even more non-hydrogen things attached, okay? The product of a tertiary alkyl halide is what we're going to call a more substituted alkene versus a less substituted alkene. Periodically, students struggle with what we mean by the term substituted. We use that word a lot. And in this context, a substituted alkene means an alkene where one or more of the hydrogens has been replaced by a carbon. So up here is an unsubstituted alkene. This is a monosubstituted alkene. And then this is a disubstituted alkene. And it will turn out that the more substituted alkenes are more stable for reasons that we'll talk about, but probably not today. And you will see that the more substituted, more stable alkenes form faster because the transition states that lead to them are lower in energy. All right? So that's the reason behind this rate issue where tertiary alkyl halides are very fast to do elimination reactions. Okay, questions about that? Yeah.
If let's say with the tertiary, one of the hydrogens that from the end was replaced with a carbon bond, but you still have the proton anti, the beta proton, would that be preferred? Does that make sense?
For the tertiary alkyl halide, if one of the hydrogens were replaced by a carbon here,
Or something. But you still have that like beta proton?
yeah, so would it be even better, that's an interesting question, would it be even better if there were other carbons here so that the alkene could be more substituted? Yeah, and we'll go through some examples of that. It's a good question. Yes?
Sorry, can you just repeat why the substitute alkene forms faster?
Because it's more stable. I didn't answer why it's more stable though, but I will at some point, just probably not now. Okay, good. Others? Okay, so maybe it would be good before we dive into a bunch of examples to just summarize where we are. And let's see, how do we do this? Yeah, so we've got now on our chart that we started last week, along the left-hand side, we're going to have 4 different categories. We're going to have a class of molecules that are both good nucleophiles and good bases. And if you want to draw some examples of things that are good nucleophiles and good bases, here's just a few of them. Then we might have things that are good nucleophiles but weak bases. And you could include perhaps some things that are on that list. Then we're going to have molecules that are weak nucleophiles but good bases, and this is going to be basically the sterically hindered ones. And then you're going to have molecules that are both weak nucleophiles and weak bases, and these would just include like water and alcohols. All right, so those are 4 different groups of nucleophiles and or bases. And then here across the top, we'll simply write the types of leaving group situations we have. Primary, secondary, and tertiary. And we'll remember that what we've learned so far is that SN2 is slow / impossible for tertiary alkyl halides because of sterics, and that E2 is slow for primary alkyl halides or primary leaving groups because they have fewer beta protons and because the alkenes they form are less stable. All right, so we'll go through for each of these 4 categories of nucleophiles and bases. We can sort of predict what will happen. For example, what would you say for something that is a good nucleophile and a good base, but for a tertiary alkyl halide? Can you do SN2? Okay, there's no SN2 for tertiary alkyl halides. Can good bases do elimination? Do good bases have to wait for the leaving group to leave? No, they're reactive enough. They can go ahead and remove the beta proton as it is. So you would expect to see E2 only in that category. Now, what if you have a good nucleophile and a good base and a secondary alkyl halide? That's a situation where SN2 is okay and E2 is also okay. So you expect to see competition between the two. You expect to see both products. I won't ask you to predict whether elimination products are better than substitution products under that situation, but I will ask you to predict that they would both happen, all right? Now, what about for the primary alkyl halides? Well, we said that SN2 was fast for those, and that E2 was slow, so we're basically going to see SN2 only. SN2 beats E2 for the primary alkyl halides. Okay, see how we're going through that? We're making that comparison, trying to decide reactivity of the nucleophile versus the reactivity of the electrophile. Okay, now good nucleophiles that are weak bases, those generally are not going to do E2. So this one's pretty easy. They're going to prefer SN2 for primary and secondary alkyl halides. Now here's the tough part. What do you do when you're with a tertiary alkyl halide and you can't do SN2, but you're also not a weak base, so you can't do E2? What option's left? You gotta wait for the leaving group to leave, and then you're gonna see SN1 and E1. Those will basically always compete. What if you have a weak nucleophile that's a good base because of sterics? Those can't do SN2, so those are going to be E2 all the way across the board. That line is easy. The good base can always remove a beta proton. Okay? And then lastly, for the weak nucleophiles that are also weak bases, you're used to doing this for secondary and tertiary alkyl halides and seeing SN1 be the answer. Now we're going to add in E1. Here we're going to say question mark, usually no reaction, but what are you supposed to be aware of? Beware of the possibility of a resonance stabilized, why can't we spell? There's no D at the end of resonance. Resonance stabilized carbocationic intermediate, which would make SN1 and E1 possible. Okay, so that's sort of your overview. Yeah?
Would you see any SN1 with a good nucleophile and a good base of the tertiary carbon?
Would you see any SN1 with a good nucleophile and a good base of the tertiary carbon? No, because the good base is not going to wait for the leaving group to leave. It will just steal the beta proton. Okay, good. Others? All right, so now we just need to do a ton of examples that illustrate all the possible problems that you might encounter. So let's do just a few. Okay, so there's reaction numero uno. So let's make a prediction. Primary alkyl halide. What would this type of molecule be? What category of nucleophile is that going to fall into? Yeah, its conjugate acid is an alkyne whose pKa is around 25. So this anion, which is called an acetylide anion, is both a good nucleophile and a good base. So that, what do you predict for a primary alkyl halide? SN2, because SN2 is great, it's super fast, but E2 is slow for the primary alkyl halide. So that's SN2 only. So you expect to get this as your major product, okay? Now, in this case, there's no stereochemical issues. You're not making a stereocenter. Yes, the reaction proceeds via backside attack and the leaving group leaves, but because the molecule you make isn't chiral, because you don't make a stereocenter when the nucleophile replaces the leaving group, there's no issues of stereochemistry to really worry about. All right? Okay, questions about that? All right. Let's do another one that will be more evil than that. Okay. You guys ever been to Moon's Rare Books at the Riverwoods? Seen all the cool stuff that's there? I was just thinking, they have a Halloween display of all sorts of weird magic books, and I'm wondering if someday, 200 years from now, whether they will display my evil notes there to scare children. I'm guessing these are not going to be useful 200 years from now, so we'll see. Maybe we'll have learned more science. Okay. Behold, a secondary alkyl iodide. And, you know what? I wanted that not to be there. It's such a good problem. It would be a good, no, let's just keep it as it was. That's good. And let's use CH3O- as our nucleophile. So this is a secondary alkyl halide. And this is something that is both a good nucleophile and a good base. So what do you predict in terms of the outcome? Competition between both SN2 and E2. So let's deal with, all you will do in this case is you'll draw the SN2 product and the E2 product or products, depending on the situation. So let's deal with SN2 first. SN2 is going to proceed with backside attack via backside attack with inversion of configuration. So the SN2 product should have the nucleophile in place of the leaving group, which was I minus, and it should have inverted configuration. So this is the SN2 product, right? Now, how about the E2 product? Here's where you want to be a little bit careful, because remember, E2 requires that the beta proton be anti to the leaving group. As you get more experience, you may be able to do this in your head. At the beginning, you should probably work with either a model set or draw some Newman projections. So I'm going to look down the bond between the alpha and the beta carbon, and we're going to draw what we see so that we can have an idea of which of these two protons that are beta to the leaving group, proton A or proton B, can be anti to that leaving group. So here is what we're looking at. I'm going to use, from our perspective here in the plane of the page, the benzene ring would be out to our right. I'm going to use the R for a benzene ring. Proton A would be pointing upward to our left. Proton B would be pointing downward to our left. Then on the other side of the alpha carbon that's in the back, the benzene ring would be coming straight out to our left. The iodide would be coming up and to our right, and then there's a proton on that carbon, another proton that's implied but not shown, that would be coming down to our right. So here is the leaving group on the alpha carbon in the back, and here is the beta proton on the beta carbon in the front. And you can see that it's HB and not HA that's anti to the leaving group. That matters because of hyperconjugation. Only HB and not HA will have LUMO on it. Okay? So you would expect a base to remove HB rather than HA. Now, here's an interesting thing. In the product, HB is now gone. It's on the base. And I minus has left. And we're going to still do this from the perspective of the Newman projection. In the product, there's going to be a pi bond between the beta carbon and the alpha carbon. So that means that the beta carbon is going to be rehybridized to be sp2. And as we look at it from the side, this is what we're going to see. And then the alpha carbon in the back will also be rehybridized to be sp2. And this is what we're going to see. And importantly, those two benzene rings are going to be trans to each other, so that if we looked at this product, we would see this alkene as one of the elimination products. And you're seeing that if we remove HB, we get a trans relationship between the two benzene rings that are in our product. We have to. Do you see how that was set by the fact that HB was anti to the leaving group? Now, is there any other conformation of this starting material that would allow HA to be anti to the leaving group? How would I get that? I can spin around carbon-carbon bonds, right? So let's take the carbon in the front and let's just rotate it, and it looks like that would be a simple 120-degree rotation. That would bring HB here, put HA here, and then that would put the benzene ring up to our left. Now HA is anti to the leaving group. So now it's the reactive proton. Remember, only the beta proton that's anti to the leaving group is reactive. So when the base removes HA, and we form the pi bond and the leaving group leaves, notice how the two benzene rings are now on the same side of the molecule, so that if we were to watch this reaction happen, we would see that we get a cis product rather than a trans product. Okay? So the two E2 products are the trans product, where HA is still on the molecule, and then a cis product where HB is on the molecule. And in general, of those two E2 products, the trans is going to be the major because it is more stable because of sterics. But the point is that the E2 reaction has stereochemical requirements and stereochemical consequences. You're seeing that if I remove HA, I get one alkene diastereomer. If I remove HB, I get the other alkene diastereomer. And you have to follow those two consequences out in detail to get these kinds of questions right. Okay, I think that's all we have time for today. So good luck on the exam, and I will see you Wednesday.